Transformers. It's a very important device that is used in power transmissions. From the power generating station, the electric power is generated with a very low voltage, but it has to be transmitted through long distances where we have to increase the voltage, and there is an adjustment with the voltages to be made for the alternating voltage. We use an instrument called transformer, and transformer works on the principle of mutual induction. We have discussed that mutual induction in detail. Now this is a practical application of what we call mutual induction. Now to discuss the working of the transformer, see this, there is an iron core is taken, this is the iron core, and laminated copper wires are taken, and we have a first winding on it, and that first winding is called primary of the transformer, and primary is usually considered as the input of the transformer. And on that primary windings there is another winding done using laminated copper wire again, and that winding is considered as the secondary of the transformer or the output of the transformer. Now number of turns of the primary I took it as NP, and number of turns of the secondary I took it as NS. Now let us see how it looks. Now suppose I apply a varying voltage as the input here, that produces a varying current flow through the, what do you call, primary coil, and that primary coil will be producing a flux, and that varying flux will be linked with the secondary coil, and that varying flux produces an output here called a varying voltage as the output. So mutual induction is coming. Now the secondary voltage obtained will depend upon the number of turns of the secondary which is coming along with the magnetic field of the primary due to the varying current flowing through it. Therefore, the secondary voltage Vs, it's an induced voltage, will be equal to minus of Ns into d phi by dt. So this is the flux linkage, and rate of change of flux for that Ns number of turns will produce a voltage that will give a voltage that is the secondary voltage. Understood? Now at the very same time we can see that the back EMF production, as the varying voltage is coming here, that varying voltage on the secondary will be coupling with the primary. There is a back EMF effect is coming, and that back EMF effect gives a value for input voltage, or in terms of that back EMF we can take the input voltage as minus of Np times d phi by dt. So this is the primary voltage in terms of flux variation. Here is the back EMF effect, and this is the secondary voltage produced by the varying voltage given in the primary. Now, taking the ratio of this, we can have Vs by Vp is equal to Ns by Np. And this is what we call transformer equation. Now, why this is called transformer equation? Because based on this we can define the transformer in two categories. One is step up transformer. Step up means secondary voltage is greater than the primary, means there is a sudden increase in the output voltage. That means if you give 100 volt here, you will be getting 1000 volt over here. Stepping up. So in that case, we can see output voltage is greater than the input voltage. That is possible N only if Ns greater than Np. So just by adjusting the number of turns, we can increase the voltage. And another thing is that step down. Step down transformer. That means output voltage, secondary voltage is less than the primary. That means 1000 volt you give as the primary and we get 100 volt output. So that is possible only when Ns less than Np. So that defines the type of transformer, therefore this is called a transformer equation. And Ns by Np, in general we can take it as Ns by Np, transformation ratio or turns ratio, we can say Ns by Np. Alright. Now, if we consider an ideal transformer, ideal transformer, there is no loss of energy. That is not possible practically, but if we consider something like that, then the input power must be equal to output power. So when I say input power is equal to output power for ideal transformer. If this is the case, then IP into Vp, that is input current into input voltage, will be equal to Is into Vs. That means output current into output voltage. Therefore, from this we can have an equation that Vs by Vp equal to Ip by Is. This is another equation we can have. So here we can find one thing that suppose the voltage is increasing, the current in that part is decreasing. So current voltage adjustment is coming. But this is only ideal case. Always the output power will be less than the input power due to many reasons. Okay. So there is always a loss of power coming, and that loss of power is due to 4 different ways as possible. One, losses in the transformer or transformer loss. So if we consider the transformer loss, first one is the flux loss, flux leakage or flux loss. That is, whatever flux is produced in the primary is completely coupled with the secondary, then there is no loss. But due to reasons like the air gap between the turns and the spacings between the same turns itself, like there is a separation spacings there between, and air gap between the primary coil and the secondary coil, all this will be causing the flux leakage in the case of coupling over here. Due to that flux leakage, there is loss of power coming. That is called flux loss or flux leakage. This can be contained by winding the primary and the secondary one over the other tightly. Okay, tight winding without any air gap, we can reduce or minimize the flux leakage. Second loss is heat loss due to the resistance of the winding. Heat loss. Heat loss due to resistance of the windings. Now you know that according to Joule's law, whenever a current is flowing through a resistance, there is a heating produced like I square R heating is produced. Due to this heating, energy is lost. So how to minimize that loss? It's very simple. Use thick copper wire for the windings. That doesn't mean that you will be making a thickness very large and what it is not, but an appropriate thickness to be considered. For that we can minimize the heat loss. Then the third one is that eddy current loss. Eddy current loss. Eddy current. What is eddy current we studied? Because the flux variation is taking place on the laminated, on the thick metallic core, and in that thick metallic core there can be eddy current produced, and due to that eddy current there will be heating produced, and therefore eddy current loss is possible. This eddy current loss is reduced by using laminated iron sheets coupled together. Means instead of taking a single thick core, slices of that is taken and laminated slices will be pasted together to make the core. That way we can minimize the eddy current loss. The last one is hysteresis loss. Hysteresis loss. Because here we are applying varying voltage, and that varying voltage is sending varying current. That will produce a varying magnetic field for the metallic core here, and that varying magnetic field will be taking that metal core through a cycle of magnetization and demagnetization. Thereby there will be a hysteresis coming, and due to that hysteresis there will be a loss possible. And that hysteresis loss is minimized by using or selecting the material for the core based on the hysteresis loop. If we take material, soft iron, we can see that that material is having a thin hysteresis loop. If the thin hysteresis loop material is taken, then the energy loss, the area of the loop defines the loss. So if the area is very small, then the loss is also very small. So you can select soft iron for making the core of the transformer, whereby hysteresis loss also can be reduced. So this is all about the transformers, and the most important thing is that this instrument works it works only in AC, not in DC. That's a very important thing to be kept in mind.